So to start, I want to first mention, for the avoidance of some confusion here, which version of Scenic we're going to be working on. As Sanjay mentioned, this project's been going on for more than 6 years now. And if you look at some of our older papers, the syntax is a little bit different. So just to clarify things, let me just describe the different versions of Scenic that exist and that you'll see maybe in some of our papers. So the first version from our original tech report and our first conference paper on Scenic only handles static 2D scenarios. So if you look in our first paper, you'll see that's why nothing is talking about 3D. And we had interfaces to GTA 5 video game and this robotic simulator Wheatbots. Then 2.0, which is the mainly described in our journal version of the Scenic paper from 2022, this added the ability to talk about dynamic scenarios. So things changed over time. We also had a major new feature, this abstract library for writing driving scenarios, where you could write driving scenarios using this library, and then they would work without changes in multiple driving simulators. So that still exists, and it's from that time. The latest version of Scenic, which is what we're going to be working with, is Scenic 3 from a CAD paper last year. The main change there is now Scenic has native support for 3D scenarios. So the syntax changed slightly to accommodate that. So if you look at examples from older papers, it might not quite work out of the box if you just try running it. One other nice thing about Scenic 3 is we now have our own parser. So the error messages are actually pretty good now. So if you do try running a Scenic 2 program, the error message will hopefully be informative. But at any rate, so that's why you might notice if you're reading some of our papers, there's a little bit of variation in the syntax. But everything from the last year onward should be using Scenic 3.0. The documentation describes Scenic 3.0, and in most of the cases where there were changes, there's a little note saying, hey, this changed in Scenic 3, just so that you're aware. There's also a page in the documentation called What's New in Scenic, which has the versions where everything was added. So if you're trying to run something and you can't figure out the right version, you can look at that. But if you just install Scenic from the repository or from PyPy, you'll get 3.0. So hopefully this won't be an issue unless you're working with older examples. Okay, so writing static Scenic scenarios. So we're going to start by looking at in more detail at this badly parked car example that Sanjay put up before. So here on the left-hand side, you have kind of a top-down schematic of the scenario we're trying to encode. So you have the ego car circled here. The blue dashed lines here are the view cone, so what the ego car can see. And we want somewhere in that view to have a badly parked car. So we have another car which is sort of near the curve, like a little bit far away, and at some kind of a funny angle. So the way we're going to build this up is in a few steps. The first thing we're going to do is import a Scenic library, which is called the world model for driving scenarios in Scenic. So Scenic itself doesn't know anything about cars or lanes, etc., because as Sanjay showed, it has many different application domains. And like you might be using it for robotics, and there isn't a notion of a car or a team, etc. So Scenic itself, the core language, just knows about geometry and spatial and temporal relationships between things. So what we're doing here is we're using Scenic's model statement to say, I want to use the following library, scenic.domains.driving.model, as the world model for this scenario. A world model, you can think of it as just a Scenic library that you import. What this model statement is doing is basically just like an import in Python, which pulls out of that model everything that's defined there. And that model includes things like a class called car. It says, okay, here's what a car is. Here are what the properties that a car has. And this one, as we'll see, will also define information about the road network. So this is a particular world model that's built into Scenic. It's this simulator agnostic driving model. But you can define your own for a particular application domain. We also have some that are specific to particular simulators. There's nothing really special about this. It's just a .scenic file, which we wrote and happens to be included with Scenic. Okay, now that we've imported that, oh, and I should say, please feel free to interrupt me at any time. Just raise your hand. Happy to take questions. If you're on Zoom, I think I can see if you raise your hand there. If I don't notice, after 20 seconds or something, feel free to unmute yourself. Okay, so then we're going to start by creating the ego car. So the car from which we're going to render these images. And we're doing that using Scenic's new statement. This creates an object of a given class. So we're saying create a car, and we're assigning it to this variable called ego. And you'll see this is highlighted. It's actually italicized here because this is a special variable that Scenic knows about. The ego is a designated object, which is kind of the reference point for the scene that you generate. So some Scenic syntax, if you don't say what something is with respect to, it'll use the ego by default. Okay, so notice here that we haven't said anything about where this car should be located, what color it should be, etc. So all of those properties, the distribution that Scenic will use on those comes from the car class. So we'll take a look at the definition of the car class later on. Basically, when you're defining this class, you can say, okay, the default position for a car should be this distribution. So in this particular example, the driving model puts a prior distribution on position of cars, which is uniform over the surface of the roads. So anywhere in the road network, but not, for example, on a sidewalk, inside a building, that kind of thing. Okay. So this car, since we haven't specified anything, is just using those default distributions to find the car class. Okay. Oh, one other thing I should mention, if you're looking at examples, we'll come back to this when we do the hands-on part later. But if you want to get this syntax highlighting, there are extensions for VS Code and for Sublime Text. Syntax highlighting, Scenic, so you can install those. And it should look similar to this. Okay. Oh, right. Rather than so properties like the position of the car, the orientation, etc. These are going to use the default values because we didn't give a more specific definition of those properties for this car. Okay. Now, this second car, we have to be a little more specific about how we want to create this one. We're going to do it in a few steps. The first thing we're going to do is pick a point on the near the curb or on the curb for the car to be parked at. So in terms of this diagram, zooming in here, this red line on the side, that's the curb region. This curb region is defined in this driving model. So Scenic has a primitive data type called region, which represents a region in space. There are lots of different kinds of regions. You can define them using polygons, sets of points, polyhedra, etc. This driving model defines a region called curb, which is the set of points on the curve in the road network that you've imported, which I'm not actually showing here. This scenario is designed to work with any road network, as long as there are some curves somewhere. So we actually can specify on the command line which map you want to use with this one. We can show that later. Okay, so what we're doing here is, first of all, we're taking this curve region and restricting it to the part that's actually visible from the ego. So this visible here is a built-in function. Oh, sorry. We're going to take that and then pick a random point on it. So the way we're doing that is we're starting from this region, curve, and we're applying a built-in function called visible, which intersects it with the view cone of the ego. So here, the blue dashed line. So of the whole red region, we're just getting this bolded black part now. And then the way that we're picking the random point on it is with this syntax, new oriented point on. So what's going on here? Oriented point is a class which is built into Scenic. Scenic has 3 built-in classes for objects, points, and oriented points. So an object you can think of as just something in space, like a car. It has a position, it has an orientation, and it has a shape, like dimensions, certain size and shape associated. Oriented point and point are kind of more limited versions of those. So a point just has a location in space, doesn't have an orientation, doesn't have a shape. Oriented point is saying there's position in space and we have an orientation associated with it. Why would you want to define that kind of thing? Basically, this is the information you need to specify a local coordinate system. So if you want to say, here's the origin and here's the orientation of the axes, that's the information in an oriented point. So here what we're doing is we're saying, take this region, visible curve, and pick a point at random within that region And the oriented part is going to help us here because it turns out this curve region has what we call a default orientation associated with it. So at every point on the curve, we also know like what is the direction the curve is facing at that point. So this on syntax here is what in Scenic is called a specifier. So when you're creating an object in Scenic, you have to say what all the properties of that object are, the position, the orientation, and so forth. And Scenic's specifiers give you a lot of different ways of specifying the values of those properties in a natural language like syntax. So the on specifier in particular takes in a region as input, and it specifies the position of the object that you're creating to be uniformly at random within that region. So here we're saying, take the visible curve and take an oriented point and put it randomly in that region. If you had a 3D object like box or something, then on puts it on top of that region. There's also a specifier called in if you want to put it inside a region, for example. And there are a bunch of more specifiers. We'll see a couple in these examples. There's a big list of them in our documentation. But what these ultimately do is basically provide values for all of the different properties of the object that you define. Okay? So the effect here is to create an oriented point which is somewhere at random within this visible curve region, so this point here, and it's going to have an orientation aligned with the curve at that point. This on specifier also deals with the alignment. Okay. So in fact, you can combine different specifiers together. We'll come back and see that in just a second. Now let's pick the angle for this car to be parked at. Here's the first place where we're going to see an explicit distribution. So we had a distribution actually here. We said pick a random point within this region. Here I'm going to say, here's more specifically a particular distribution I want to use for the angle that this car should be parked at. So I'm going to say pick an angle first, uniformly at random between 10 and 20. So the range function here is a built-in function in Scenic, which provides a uniform distribution over a range or an interval. And now I'm multiplying that by a uniform choice of either 1 or -1. So that's to give us an angle which will be to the left or the right, up straight ahead. Okay, so now this bad angle is a random variable, which is uniformly at random between 10 and 20 or -20 and -10. All right. Oh, and I guess I didn't mention it, but this degrees here is just a built-in postfix operator in Scenic, so you can write things in degrees if you don't want to do negatives. Oh, yeah, Mary.
Case was oriented to follow the flow of the visible curve.
Yeah, so I didn't really show that here, but this curve region, it turns out, we defined it in such a way that at every point on the curve, we say the preferred orientation at that point is like parallel to the curve. And so this oriented point that we're creating here, a spot, is going to inherit that. So it'll give you a point like this point, and the orientation is like along the curve here and kind of upright. So like if you imagine a person standing at that spot, facing along the curve, that's the orientation that this spot is going to have. Okay, so now let's create this badly parked car, and we're going to do this using two specifiers. So first we're going to say where we want to put the car, the position property of the car. Going to specify that with the left of specifier, which does what you would expect. So it takes this spot and it's going to move half a meter to the left. Now, one notable thing here is if you want this gap between the car and the curb to be half a meter, you need to know how wide the car is, because the position of the car is represented by its center in Scenic. So if this car were wider, we would need to put the center of the car further out, have this half a meter gap. So actually, this left of specifier depends on another property of the car, its width. So this specifier, if you look at the documentation, like under the left of entry, it'll say it specifies the position property, and it depends on the width property. So specifiers can have these dependencies where they will specify certain properties in terms of others. And Scenic will figure out the order in which to sample all these things so that it can be evaluated and you end up with an assignment of distributions to all these properties. Or if you have a cyclic dependency, it'll give you an error. So in this case, Scenic knows, okay, I have to figure out what the width of this car is before I can actually evaluate this left of spot by half meter. And the width of the car, we're not going to specify this, so it's going to come from the default distribution, which in the driving model, I think what it does is it actually, the width depends on the model of the car, and the model of the car is a choice from a bunch of random car types. So it says basically, okay, pick the car type out of 15 types of cars, then look up what the width of that model of car is, then we can evaluate this. Okay, so that's the first specifier we're going to use. Oh, question. Yeah.
So here the center of the car is 0.5 meters to the left, or
sorry, the center, the right edge of the car will be half a meter over. Yeah. If we just wanted the center to be half a meter over, you couldn't use this left of specifier, because left of by default takes into account the size of the object, because that's usually what you want. When you say it's half a meter to the left, you mean there's a half a meter like gap between the two things. So you could also write it so that the center would be half a meter over. We can show that in the hands-on part if you're interested. But yeah, it's the right edge of the car will be half a meter. Specifically the center of the right edge, because the car might not be a rectangle. I'm showing it as a little bounding box here just for simplicity. But Scenic now handles objects of any kind of different shape. Okay. So now to specify how this car is oriented, I'm using another specifier, face. So the facing specifier just takes an orientation and position or aligns the object to that orientation. So here the orientation we're using, I'm building up in a couple of steps. So we're starting from this road direction thing, which is another object defined in the driving model here. This is an instance of a primitive Scenic data type called a vector field. So we had regions before that indicate regions in space. Vector fields, they say at every point in space, what is some orientation at that point. So you can use it to represent things like, what's the driving direction on a road? So depending on where you are on the road, you should drive in a different direction. Vector field gives you that kind of information. You can also use it for things like, on the surface of an object, what are the normals? So how should you orient an object so that it lies flat on this surface, this irregular surface? So what we're doing here is we're saying, I want this badly parked car to face this angle that we chose before, but not in the global coordinate system. In Scenic's global coordinate system, an angle of 0 means due north. But if this road is not pointed north, like here it's slightly over, we want a 0 angle to mean pointing along the road. And we want like this positive angle to mean tilted one way versus the road, and negative would be the other way. So here what we're saying is facing bad angle is relative to the road direction. So relative to here, okay, the question is the same. So relative to here is an operator built into Scenic, which says, interpret this angle relative to the road direction. And one thing to notice here is that this road direction defines a position at every point on the road. So Scenic knows here we should use the position of this car that we're defining to evaluate the road direction at that point. And then you can see relative to that direction what this angle is. Question.
Yeah, so I know this is for static scenario, but if in a dynamic scenario and the road is curved,
right?
Does it update the road direction all the time?
Good question. So for people on Zoom, just to make sure you could hear that, the question was if you have a dynamic scenario where things are moving around, with this like road direction, I could be updating, as the car is moving. Right. So the road direction itself is a static object because it says at every point on the road, what is the direction? But if you evaluate that at the position of this car, like at every time step, that would update because you'd be looking up the road direction at different positions.
So it's like a map.
It's like a vector field. So it's a function from a position to an orientation. It assigns a vector, this orientation, to every point in space. Yeah. So in fact, when we talk about dynamic scenarios, this is how some of the behaviors that are built into the driving model, like we have a follow lane behavior, says the car should follow a lane. The way it works is by looking up this vector field at the current position to see what's the correct direction I should be pointing, and now we'll try to align ourselves that. Actually, it does. I have to just double check if it does that because it's also trying to drive towards the center line of the road. So it's not just stay parallel to the road. You also want to try to be as close as possible to the center line of whatever lane you're trying to do.
So,
Yes.
here, what's the difference between an oriented point and a vector field?
Yeah, so an oriented point is like a specific point in space, like right here with an orientation. A vector field is something that says at every point in space, I give you an orientation. So if I took a vector field for example, like the road direction, then maybe at this point in the road, the correct way to drive is this way. You drive further along the road curves. Now the correct direction to drive is this way. So at different points in space, you might get different orientations. An oriented point, it represents a specific point in space and an orientation at that. That makes sense?
Yeah.
So basically, like you can think of a vector field as defining an oriented point at every point in space, whereas a specific oriented point is just one point together with an orientation. So it'd be like saying the car is here and it's facing that way. Any other questions? Yeah.
So what exactly is, are you actually sampling the map as well?
So yeah, I haven't shown here how we specify the map.
Yeah.
So in the driving model, you have to actually specify basically at the top of the file or on the command line. We'll show that later, which map you want to use. We don't actually have a way to select like a random map. You could do that if you wanted to, actually. You could write a little bit of extra code. But the thing we have built in, you just specify the map you want to use. The main road format that Scenic knows how to interpret is called Open Drive. It's a standard road network format, which Carla, for example, can also read. And so the driving model contains code to read one of those files and create this curve region, the road direction object, all these things. So that I'm not showing in this code here, saying
Right.
which map.
So the sampling done here is basically just the objects in the map.
Exactly. We're fixing the map and we're saying, let's put down these two cars somewhere within it. You could also basically put a distribution over maps if you wanted to, but we don't have anything built in to make that particularly easy.
Just to make sure I understand the last statement. Does it first create the new car like the angle along the road direction, so like along the curve, then it either like just tunes to the bad angle, so either it's just the left or right depending on what the bad angle becomes. Okay, so in that case it's like this is the left. But it can very well like shift to the right, like rotate to the right.
Right. So what this is doing, it's not actually picking like a specific position and angle for the car. All of these things are random variables. So what the semantics of this program is it says, okay, bad angle has a particular distribution. The position of this car has a particular distribution which depends on that. Well, the orientation of this car has a distribution which depends on this bad angle. It's actually in a separate step where we would sample from this distribution and get concrete angles and positions and so forth. So the way that Scenic internally is going to evaluate this, it says, okay, I'm defining a new car here. We need to know what the distribution on its position, its orientation, color, width, all these different properties that the car class has. And I have two specifiers here. The left of specifier is going to determine the position, but it depends on width. The facing one is going to determine orientation, but actually this expression in here depends on position. So then Scenic figures out, all right, the first thing I need to do is sample which type of car this is. Then I can figure out what the width of the car is. Then I can evaluate this to get the position of the car, and then I can evaluate this to get the orientation. So it figures all of that out internally, and what you end up with is a specific distribution on what the position and orientation and other properties of this car are. And then we can sample from those to get the actual values. Does that answer your question? Yeah.
Do somebody else zeros.
Oh, yeah, Kaustaf, go ahead.
Hi, yes. Hi, thank you. I've actually got two questions. First is the visible keyword that you used. Does that automatically understand that I'm talking with respect to the ego vehicle?
Right. Yeah. Good point. I forgot to mention this before. This is one of those cases where if you leave something unspecified, Scenic will use the ego by default. So when I said the visible curve, visible with respect to what, right? So I didn't say, so we're using the ego car by default. And I also didn't say, like, what's the camera angle that your ego car has. So we're using default values for those. You can customize all of that. There's also a visible from function in Scenic. So you could say that, like, curve, I think it's curve visible from taxi or something like that. And then it would give you the part of the taxi which is visible from, or part of the curve which is visible from the taxi. So this is kind of a shorthand for that, where you don't have to say it's with respect to the ego. It's just understood. That is. Does that make sense, Kelstar?
Yes, it does. Thank you.
Actually, before we go on to your second question, I'm going to follow up.
Yes.
Yeah.
So here, for example, if an object is blocking the curve, would that block the visible thing?
Yeah. So another good question is, does this visible part take into account occlusion? So what if there was like some big, gas truck here or something, so that the ego can't actually see this part of the curve? So I believe the answer is this visible operator does not take into account occlusion. Is that right, Eric?
Yeah.
Eric's nodding. Okay. This one doesn't take into account occlusion. Basically, it would be difficult to do that technically, which is why we don't do it. However, there is a different, Scenic does take into account occlusion in a different step. So you can require that some object be visible from another object. We'll talk about requirements a little bit later. And then Scenic will do like ray tracing to make sure it actually is visible. But in order to do that, we need concrete like positions for everything and orientations first. So that's done after sampling. So this part, we're defining this scenario. There's no sampling going on yet. We're just defining the distribution. But then after sampling, Scenic has a second pass where it will check to see were any requirements that you imposed on the scenario satisfied. Scenic lets you impose declarative requirements. So you could say, for example, object A must be able to see object B. And at that point, Scenic could do a more precise visibility check, taking into account occlusion. Aaron?
Because it's a little confusing, we have a page in the documentation specifically on how the visibility system works, laying all this out.
Yeah, great, thanks. So, just to clarify, in case that didn't come out well on the recording, Eric's pointing out we have a whole page in the documentation on the visibility system that talks about this in more detail. Anirban?
Is there a way to import a map? For example, then you can know where those cars are and how far.
Right. So in this example, we're positioning these two cars and there aren't any other cars. If you had like fixed obstacles, like you have some cars in known locations, this is something that you can set up in the world model for the particular scenario simulator you have, if the map is fixed. Or if you're loading it from a file, you could read that file and interpret that. So this is one of the things that the driving model does, is it can read this open drive format that specifies road networks. That doesn't include any cars built in because it's just specifying roads. But then Scenic will define things like curve, road direction, etc. We have other interfaces to simulators that have pre-built like worlds in them. So for example, Mary recently developed an interface to the AirSim simulator. And there, that interface extracts what are all the pre-existing buildings and things like that. Where are they? So that Scenic can then ensure you're not putting an object, halfway into a building or something.
So if I have a map, so this car will be already known part of the map?
This car is being added. Like this is a new one that's being created on top of whatever pre-existing simulator world you have. But if you have pre-existing objects that you need to reason about, or you want to position things relative to those, you can also define those. Yeah.
Thank you.
Okay, so Kaustav, you had a second question, I think?
It's regarding the last line actually. So you mentioned multiple specifications, I feel, at the last line, and I was wondering the order of which they will be imposed. Is it right. Determined within the Scenic program, or is it like as you specify?
The question was the order of evaluating these specifiers. So here I put the left of one first and then the facing one. But actually in this example, as I mentioned, like the left of one actually has to be evaluated first before the facing one. If I had flipped these two, it would work in the exact same way. It's actually the order of the syntax doesn't matter. Scenic figures out the order of evaluation internally. So you can put these in any order. I just wrote them here in this particular order, but the other way around would work exactly the same way. The Scenic program would have the same semantics. You just have to put them in some order, but it doesn't actually matter. Scenic itself figures out an appropriate order in which to evaluate them. If there is no order, like there's a cyclic dependency, like the position of the car depends on its orientation, which in turn depends on its position, then you'll get an error. Otherwise, any permutation of them will yield the same Scenic program.
Yeah, thank you. That answers.
Okay, any other questions so far?
Quick time check. It's about 10:10.
Okay, yeah. So let me mention one more thing about this. So this is actually a complete Scenic program. You can find this example in the repository. You can run it. It works. A few things that are going on here that aren't explicitly written out, but that I want to mention. The most important is that there are some hard constraints that Scenic imposes over this program by default. So Scenic knows, for example, that two objects cannot intersect each other, at least ordinary objects. If you wanted to find some kind of object that can penetrate some other object, you can override this. But by default, Scenic ensures that objects never overlap. So, for example, these two cars, even if we picked some spot on the curve that was like right next to the ego, suppose the ego was like facing sideways, so it was pointed straight into the curve, we will not position a car that would actually intersect the ego. So that's checked in this second pass that I mentioned before. So the way that Scenic works, we'll talk about the internals tomorrow more. But basically, you can think about this part of the program as defining these distributions. And we sample from those, we get positions for the objects, orientations, colors, all their properties. Then Scenic does this check for all of the requirements, like non-intersection. And in the worst case, if the Scenic sampled something that violates one of those, we'll reject it. We'll sample again. So we use rejection sampling. And we keep sampling until we find something that satisfies all the requirements. We'll talk a little bit more tomorrow. Scenic actually does something a little more smarter than this, but that's the basic idea. So things like cars not intersecting each other. The driving model also puts a default requirement on cars that they have to be contained in the road by default. If you want to put a car on the sidewalk, you can, but you have to explicitly say that. By default, cars are constrained to be on the road. And in this particular case, I think in the original version of this, we also had a requirement that the ego can see the other car. So even if there were some, like a big tree here or something that occluded this thing, now we would do some ray tracing to check, like you actually can see the other car. Okay. And the user can also define their own requirements like this. We'll see that a little bit later. Yes, question.
Why is it a requirement that the ego can see the other car?
That was one that we had by default. So in the first version of Scenic, where we were generating static images, primarily, there it made sense that all the cars you created had to be visible because otherwise they wouldn't affect the images you were generating. Now, actually, the latest version of Scenic, that requirement is now off by default because you might want to have a car around the corner that drives in front of you, right? So Scenic no longer requires by default that objects are visible from the ego, but you can add that requirement if you want. Any other questions on this example? Okay, so here's what you get out of this. So if we take that Scenic program, it defines a distribution over the properties of those two cars, also some global parameters like time of day, weather, etc., that we didn't specify, so they have default values in the driving model. If you take those distributions, you sample from them, you get concrete values for everything, then you can import that into a simulator. This is using the interface to the video game GTA 5 to generate images rendered from the point of view of the ego car. And you can see in these 4 different examples, all generated from that same program, that we get a car which is by the curve, but it's not quite parallel. But there's quite a lot of variability in other things, like the distance between the camera and that car, the time of day, the weather, etc. So it gives you an idea of how you can define, in some ways, a pretty specific scenario. There's a badly parked car, but leave a lot of variability in that so you can generate many different instances of that. Questions?
So in the last example, you set a uniform distribution? Can you set other types of distributions?
Yes,
to this?
great question. So Scenic has a bunch of different distributions built in, Gaussian, uniform, discrete, etc. And there's also a way to define your own distributions. If you have some complicated kind that is not easily expressible in Scenic, you can write some Python code describing how you want to sample stuff. So if that's something you're interested in, we can talk about that tomorrow when we do the Scenic internals stuff. Other questions on this one? Okay. So then, in the last 15 minutes or so here, I will show you the notebook we have based on this kind of scenario, which you can play around, you'll be able to play around with this afternoon. So if we go back, whoops. Okay, so if we go back to our workshop page here, the first schedule. Okay, so here we are in this part of the schedule, and here's the Colab notebook that goes with this. So if you fire this up, this is a self-contained Google Colab notebook, so you can run things in it without having to install Scenic, anything like that. I won't go through that part here, but if you try this later this afternoon, oops. That is good. Thank you, Eric. Okay, so there's a couple of cells towards the beginning for getting things installed. And run this. And after that, there's another one that basically registers something in Jupyter so that we can render scenes from Scenic and insert them into the notebook. So we'll let that run. And then these start with some simple examples walking you through the basic constructs in Scenic. So we're starting, for example, with this very simple Scenic scenario. We're just going to create a single object, and we're going to have its width range from 1 to 3 uniformly at random. We're not saying anything else about this object, so it's going to be a featureless cube. Okay, but then the range from size will be from 1 to 3. Oh, wait a minute. This one got modified. Okay, I'm not sure how that got messed up. This one's not supposed to actually have the width.
That's great.
That's later.
This new object.
That's funny. Not sure what happened there.
Well, I was playing with it. I don't know why it should update.
Oh, you
shouldn't
didn't make a
update
copy of
everyone.
it. But you have write access.
I have
So
write access.
that's
Okay,
oops.
sorry.
Okay. We'll clean that up before this afternoon. But anyway, okay, so new object. So I just ran it, and here it is in Scenic's visualizer. Of course, for generating real data, you want to connect this up to a simulator. But for debugging purposes, Scenic has a very simple visualizer just so you can see what's going on. So here's the scene. There's the cube. We can click and drag to see different angles. We can zoom in and out. It's just a cube. Not too interesting.
Question.
A question, yes.
What are the properties of this object defined?
Yeah, so this one, we didn't specify any of the properties. So it's using the default values. So if we go over, for example, if we look in our documentation. Oops, that's a different page.
Just scenic.org and then click on documentation.
Okay, so if we go to the main page, right, and you click documentation here, you'll see we have lots of documentation here. We have some tutorials, which basically are expanded versions of what we're doing today. But there's also a helpful syntax guide, which summarizes all of Scenic syntax in one page. If you click on that, you'll see there are a bunch of different sections. Primitive data types, distribution. Here are like the different kinds of distributions that are built into your question. Let's go down to the objects section. And it says, here's how you create an object. Here are all the properties that objects have and their default values. So in particular, the default value for position is the origin. So we didn't specify the position, so we're going to get something at the origin. The default orientation is basically given by these yaw, pitch, and roll angles, which are all 0. So it's going to be aligned with the global XYZ axis at the origin. And for example, the width, default width is 1. So and length and height also. So you're going to get this unit cube centered at the origin. Okay, but we can change this to make it a little bit more interesting. So here's one. Now we're going to start playing around with some of those properties.
So this is the same notebook that you're going to use in the afternoon, right?
Yes, exactly. So I'm just showing a couple of the things just so you can see how
So
this.
you don't have to follow.
You don't have to
step
do
by
it
step
live right now.
right now.
We'll give you time in the afternoon. I just want to show you how it's going to work so you can get started later. So in this example, I'm going to create a new object. Now I've added 5 specifiers. So we've set up this notebook so that when you run Scenic code, it'll print out a syntax highlighted version because we haven't yet figured out how to highlight it within the notebook code cells itself. Hopefully by this afternoon, you'll all have Scenic running on your local computer anyway, because we're going to have time to help you out with this before lunch. And then you don't have to run these in a notebook. You can run it in your own machine. And then if you have like VS Code or Sublime Text, you can have it syntax highlighted as you're running it there. I'll show that before we head to lunch as well. Okay, but anyway, here's the syntax highlighted version. So we've got a new object, and now this time I've done 5 specifiers here. The width specifier is the most basic specifier. It just says set the given property to the given value. So here I'm saying with shape, cone shape. So shape is a property that's built into Scenic that describes the shape of the object. You can use a mesh to define the shape of the object, or you can use various primitive shapes that are built in just for simplicity. So cone shape is one we put in there just so that you have it. So we're saying it should be a cone with width 2, length 2, height 1.5, and it should be facing the following orientation. And we're giving it with a set of 3 yaw, pitch, and roll angles. So if you're familiar with like aircraft, yaw is rotation like left and right. Imagine I'm like the airplane facing forward. Yaw is left or right, using the right-hand rule. So positive yaw is turn left. So as viewed from above, it's counterclockwise, like right-handed rotation. Pitch is up or down, and then roll is along the axis of the object. Roll. This is all described in Scenic documentation. If you can't remember that, don't worry about it. But that's what we're doing here. So we're saying apply negative 90 degrees of yaw. So that's turning 90 degrees this way, then 45 degrees pitch up. Since there's only one object here, you can't really tell what that is. It's not so easy to see what that's going to do. When you create multiple objects, this will become clearer. But here we go. We get this cone. Let's do one. I'm going to skip down to one of the 2 objects. Oh, here we go. Here, the next one has 2 objects. So now we're saying create a new object, the ego. So this will just be at the origin, a cube, unit cube at the origin. And now we have this cone shape that I did before. But now let's use that left of specifier to position it. So we'll say left of the ego by 1 meter. Okay. Scenic doesn't actually it doesn't know about units. You can interpret them however you want. Typically, it means meters. In I think all of our simulator interfaces, they use meters. Okay, so if we sample from this, there we go. We've got the ego over here at the origin, and 1 meter to the left of it, we have this cone. If we rotate down here, you can see it's been turned. You saw it had been turned to the left 9 degrees before, and it's also been pitched 45 degrees up.
So what length is 1 meter here?
So which way is the cone? So I think, the 1 meter. So that's from the top down. Let me just resample this. This is 1 meter from the left edge of the cone to the left edge of the cube to the right edge of the cone's bounding box.
So there's a bounding box on top of.
Right. So Scenic, the left of specifier uses the bounding boxes of objects because it would be basically too difficult to figure out the exact distance. I mean, Scenic can compute the exact distance once you've positioned things. But if you wanted to say left of it by 1 meter, taking into account the exact shape, that would require Scenic to know the shape and the orientation. Because depending on which way it was oriented, a different part of the object might be closest to the first. And that would make it very difficult to get these cyclic dependencies of the position, the orientation, depending on each other. So for that reason, this left of specifier does this approximation using the bounding box. Eric?
But I should add, is something that's come up before where you want to place objects like that are irregularly shaped flush on a table, for example. And so we got like some helper functions that we're working on that
Right.
can help mimic that maybe sacrificing some like absolute randomness. And we'd be happy to talk to you and spend that off.
Yeah. So if you're working with objects that are very non-rectangular, right? Like imagine like a robot that's mostly rectangular, but then it has like a long probe sticking out or something, right? So it's not very well approximated by its bounding box. Much of Scenic will use the exact shape, like collision detection will use the correct shape, occlusion checking will use the correct shape. But a few things like left of like this, for practical reasons, they need to use the bounding box. So if you needed to position something else, like something where it was inside the bounding box, but like maybe you wanted it to be like to the left of that probe, like inside the bounding box, this left of wouldn't work. But we can talk with you offline about ways to make that work using a more complicated mechanism than this left of specified. Question.
Is the camera location you predefined in this case?
So in this built-in visualizer, the default is just looking straight down from some height. I don't actually know. Maybe it's just, I think, just high enough so that you can see all the objects. I don't remember exactly what it is. It's just a heuristic for visualization purposes. So I think tomorrow we'll talk about how you actually generate synthetic data from Scenic when you're connected to a real simulator. And there you can specify, all right, I want the camera to be here. Here's the resolution. Here are the angles. These kind of things. Yeah.
But when we say left, it does left compared to the camera, right?
Oh, left means compared to the ego. Yeah.
Oh,
so it's left of whatever it is that you're specifying here. So it looks at the ego, and it looks at the way the ego is facing, and then it's to its left. Yeah. If you wanted to do left in the global coordinate system, then you would have to write something a little bit different. This is left relative to the ego.
Let's see.
Yeah.
Is there a way to specify your own bounding boxes?
Yeah, so when the question was, how do you specify the bounding box? So when you're creating an object, you can specify the shape. So we had this example here, like with shape, cone shape. There's actually a little blurb up here that's hidden by default. If you want to know, like, how can I import a mesh? Like I made in some 3D editor, I made this complicated shape. How do I get that into Scenic? This is described here. And then Scenic will figure out the bounding box for that. Thanks. So we have a few meshes for like chairs and airplanes and things built in for some of the more interesting examples. So since we're almost out of time here, I'll just show, you can look through this later when we do the hands-on part, try some of the more complicated examples. This walks through how you can like position objects on top of other objects. Take something like, say, maybe I have a plane, put some object some distance in front of it, and then project it down onto a surface, that kind of thing. Yeah, this goes through all of that, and we have some exercises built in as well. Okay, so let me just wrap up by showing you one of those more interesting ones, just so you can see. Okay, here it is. So this is an example where we're saying we're making this 10 by 10 floor, 10 unit by 10 unit floor, and then we're going to create this airplane in the corner up here. So it's like 3 units over, 3 units over, 10 units up, facing 135 degrees. So it's 0 being north. This is like southwest. So you get this object here. And now we're creating this new object ahead of the plane by a random distance, 2 to 5 meters, but on the floor. So if you look at the top-down view, you can see this cube is being positioned straight in front of the plane by some distance. If I resample this, we should get a different distance. There you go. It's further away this time. But now if we rotate this, you'll see the plane is 10 meters up in the air, but the cube is on the floor. So this is a more complicated example where you can see here we're combining 2 different specifiers for position. That Scenic lets you do this. We're saying ahead of the plane by a given distance, but then this on specifier projects the resulting position down onto the floor. All right, so I think we'll stop here. This gives you some sense of the main features in Scenic for specifying scenes, static scenes. We'll have our coffee break now, about half an hour. We're happy to take questions if you have some. And then we'll talk about dynamic scenarios after.
Check if there's any questions online.
Oh, yeah. Were there any remaining questions from Zoom? Yes, not. Okay, so Zoom folks will keep the call running. We will return in half an hour.